All right, I'm really excited about today's class, which is diffusion models, also called diffusion, denoising, probabilistic models. This is a very important algorithm. As far as I'm concerned, it is probably the mathematically deepest algorithm within all of artificial intelligence, and it also happens to have one of the most significant applications thus far. It will change the world, and it already has started to do so. Anything from any text to image algorithm that you've ever played with, if you've seen the DALL-E 1 through 3 or Sora, we're talking about being able to describe a scene or an image in your head, type it in a prompt, and then suddenly you see a video or an image of that come to life within seconds. If you've ever wondered how that's done, today's class will explain all of that in its mathematical detail. So let's dive right in. All right, diffusion models. Diffusion models, also sometimes called DDPMs, diffusion denoising probabilistic models, they work a certain way based on a certain idea. And this idea comes from non-equilibrium thermodynamics, statistical mechanics in the world of physics. In particular, in 1997, Christopher Jarzynski, while on his postdoc, during his postdoctoral work, showed a certain equivalence. And the short version of the story is that, in effect, when you look on the microscopic level at something, and there's a diffusion process in particular that's occurring, right? The arrow of time is not discernible in either the forward or the reverse direction. What do I mean? I mean, if you were, for instance, very small, if you were the size of a molecule of water, and also you were able to look at very short lengths of time, and there's a cube of ink that's dropped in a bucket of water, you would see the ink diffuse in various directions, but you can't tell whether it's going away from a source or coming to a source. From your perspective, you can't tell reverse from the forward from the backward. And that is the centralized principle, the fact that the arrow of time is indiscernible or indistinguishable in the forward versus in the reverse. That is the basis for the diffusion models. In particular, it works like this. Let's say you have an image, a picture of a house. This is my picture. I'm going to put the house inside here like that. Very good picture, very clear. Let's call that X naught. X naught, we will denote the state of the system using that. And the idea is that you can destroy the structure gradually by added diffusion through sampling of random noise. What do I mean? So this picture has various pixels, right? If on each subsequent step, what I would do is I would have a way to just move each pixel a little bit. Sometimes you might not even move the pixel, but this is sort of a random process that is applied gradually. And that gradualness is necessary from the physics. This is essentially what is called a quasi-static process. It's a Markov process whereby you're not moving things too fast, because when you make things happen too fast, from the laws of thermodynamics, entropy always increases. So such processes are not reversible. So instead, what we're going to do is we move things slowly enough that it complies with these laws, and therefore it is reversible. And therefore, what we will be doing in the forward direction, we would be able to use, basically create training data that we would use to learn on the reverse direction. So this is the first state. And then we diffuse things a little bit, we scatter it a bit, and I'm going to get then to a state X1 where things don't look quite as neat, but I can still sort of tell the structure. I've just moved things a little bit, but not too bad, such that I can't recognize the house. I still sort of see its structure there. This is a state X1. And to get here, as I mentioned, there's this random process of sampling. We denote this by Q. And what I will be doing is I will be drawing random samples for each pixel. Yes, so this will give me the state of X, the probability of getting here to X1 state from state x0. All right? And this is going to be a probability, and there's going to be an equation for this, which we'll look at. That's key. And then I do it again. Again, now I would be drawing from, I would be getting to x2 given x1, and so on and so forth. And this is state x2, and things look a little more scattered. It's might be a little harder to tell that that was a house. You keep doing this until you pretty much get to random noise. So let's say there's some final state x sub t, dot, dot, dot. This is your final state. T can be any number. It's a model parameter. And at this point, you know, everything is just basically noise. And so this would be going from, you know, state x sub t minus 1 to state x sub t. Eventually you get here, and this is an isotropic Gaussian. It's just noise, all right? So if this process, this process is done in a certain way to comply with the notion of reversibility and the constraints that are required. Largely, you can reverse the process, learning the noise that you added in the first place. So now, the question I have is, now that we see the process, right, and it makes sense, so that's it. That's basically what's going on is you have your training data, an image that you feed in, and then you sequentially destroy structure by, for each pixel, sampling the pixel and creating the new location of the state of that pixel, and it would be somehow centered about a Gaussian that is centered on the prior state. So it's not completely random, right? That's why you can still see that, yeah, I can see that that's a house, you know, and then here it's a little harder. You might say maybe a house, but at this point, all bets are off. It's now just an isotropic Gaussian. So the description for this process, this forward process, is called the, as the name implies, the forward process, while the backward process is called the reverse process. And the forward process generates for us training data, while the backward process is the training process, where at the end of it, we would end up with a neural network. So the objective of this class would be essentially to derive the loss function whereby we train this neural network. And of course, you might already have guessed, once you see processes like this is actually called a thermodynamic process, and you see distributions, and you hear the word sampling, you already might start to see that, this is probably going to be similar to what we did and saw with generative adversarial networks as well as with variational autoencoders. And you would be right, okay? We would be using variational inference in this process, and our good friend, the Kullback-Leibler divergence, as you might have guessed, would also be playing a role. All right? So good. So this is our objective function. This is the loss function for diffusion models. If you're ever inspired by Sora or Kling or Imogen or DALL-E 1, DALL-E 2, and 3, and so on, now you know exactly what the mathematics is that describes all of those processes. And this is it. It's from variational inference. And in particular, this is a proxy minimizer. When we minimize this, we by proxy minimize the negative log likelihood of our data. And we're able to get highly realistic images, text to video. Sora was about a minute long. I assure you, within a couple of years from now, with the amount of resources going into AI, we would see full-length movies that you can create from home by simply just describing them in words, by voice. You don't even need to write them down, I'm sure. And bam, you'll have a full-length feature film. And it all comes out of this type of math. So beautiful. So what did we say? In quick review, we noted that of these terms on the right-hand side, the process would be driven only by this third term. Why? Because this is a KL divergence between two isotropic Gaussians. White noise is white noise. This is the final step of our diffusion of our forward process and the initial step of our reverse. So this one, negligible. What about this one? This is just a single step. It's under our control in our variance schedule. It comes out of our neural network. So this you can also ignore because we can control it and make it as small as possible. And in effect, what this comes down to is that this final term will drive that. It's worth writing out explicitly so that we see what the objective function is that we're working with. And then we can then go ahead and play a little bit more with more specific forms, with Gaussian forms in the next part of this class, and get down to the actual code, the actual pseudocode that runs this.